Hi, in this video, I'm going to teach you how to solve the Chinese Postman problem using the route inspection algorithm. So suppose we have the following graph that represents the roads and corners or intersections of the roads. And the Chinese Postman problem requires that a certain postman starting from the post office needs to travel all the roads in our graph and be able to return in the graph on the shortest possible route. So let's begin. So when you want to find the shortest possible route which covers or traverses all the roads from a starting point and then back to that original point, we follow the route inspection algorithm. So these are the steps in our route inspection algorithm. First, you need to find the total weight of the graph. So we can see that the total weight of the graph are as follow. So just add all the weights. So we have 1 plus 5 plus 5 plus 30. And then plus 5, 5, 15, 6, 12, 6, 2, 10, 3, and 4. So if we add all those numbers, we get 109. So currently, the total length of the roads in our graph is 109. So that will be the minimum length that the postman will travel, since the requirement is the postman need to travel or traverse all those roads. So the next step is to find the degree of each vertices for us to determine if we have odd vertices. So starting from the post office, so we have 3. Vertex B is odd with 3 edges connecting to them. Vertex C is also odd, 3 vertices. Vertex D has 1, 2, 3, 4, 5, 6 vertices, edges rather, connected to it. Vertex E has 3. Vertex F has 4, vertex G has 4, and vertex H has 2. So all in all, we have 4 odd vertices. Vertex A, vertex B, vertex C, and vertex E. The rest have even vertices. So we list these vertices. So the odd vertices are as follow: vertex A, vertex B, vertex C, and vertex E. So the next step is to pair these odd vertices and find the least additional weight on that particular pair of vertices. So we have multiple scenarios. Uh, we can pair AC. So if we pair vertex AC, then the other pair will be BE. So that's one scenario. Another scenario is we can pair, instead of AC, we can pair AB. So if we pair AB, we're going to pair C and E. So we can have A pair AB and pair CE. Or we can also pair A and E. So if we pair A and E, so we are going to pair B and C. So total, we have 3 possible pairings. The pairing ACBE, the pairing ABCE, or the pairing AEBC. So let's check the additional weight due to this pairing. So first we have AC and BE. So if we have AC and BE, we need to find the shortest path possible from A to C and from B to E. So looking at our graph, the shortest possible route from AC is this route. Now, if you have a more complicated graph, what you can do is you can perform Dijkstra algorithm. If you still don't know how to perform the Dijkstra algorithm, I suggest that you visit the other video explaining how to perform Dijkstra algorithm. But anyway, for a simple graph like this one, we can do this manually by inspection. It is clear that the shortest path from A to C is the direct distance or the direct path from A to C. So we write here the path A to C and the length of that path is 5. For B to E, we can see that there are numerous possible path we can take. We can take this path and that gives us a length of 17. We can also take this path and that will give us 1 plus 5 plus 6, a length of 12, which is shorter than the first path that we found. Or we can also use this path. That's 5 plus 3 plus 2, which is 10. And that's still shorter. Now, you can also find other path from B to E. But again, if the graph is more complicated than this one, you can always use Dijkstra algorithm to find the shortest path from B to E. So to be sure, let's perform the Dijkstra algorithm to find the shortest path from B to E. So we start from B. We're going to label it 0 sub B. Now, the vertices that we can visit from B are A. So we're going to label it 1 sub B. D. So we're going to label it 5 sub B. And F. So we're going to label F 5 sub B. Now, the rest of the vertices cannot be visited directly from B. So we're going to label that with infinity. So we look at the labels and see that A has the least possible label. So we will now make this label permanent. And then we visit A this time. From A, we no longer need to go back to B. So from A, we can go to D. So that's 1 plus 5, 6. But the label of D currently is 5B, which is smaller than 6. So we will keep that label and disregard 6. We can visit C. So from A, that's 1 plus 5, 6, which is smaller than infinity. So we're going to change it with 6 sub A. The rest cannot be reached from A, so their label will remain the same. Now currently, the next smaller labels is the label of D, which is 5, or the label of F, which is also 5. At this point, we can either choose D or F. It doesn't really matter. So I'm going to choose D and going to permanently label it as 5B. From D, I can go to F. So that's 5 plus 15, 20. But that's bigger than 5. So I'm going to keep 5 and disregard 20. We can also go to G. So that's 5 plus 6, 11. So I'm going to replace this with the smaller value, 11D. E from D is 5 plus 12. So that's 17. So I'm going to replace this with 17D. I can also go to C. So 5 plus 30, 35. But the label of C is 6A, which is smaller. So I'm going to keep 6 and disregard 35. Now, from all these labels, The smallest is 5B of F. So I'm going to permanently label F as 5B and then visit F. From F, I can go to H. So that's 5 plus 10, 15. So I'm going to replace this with a smaller value, 15, coming from F. To G, from F, 5 plus 3 is 8, which is smaller. So I'm going to replace this by 8 coming from F. C and E cannot be reached from F, so their label will remain the same. Now, of the 4, the smallest label is 6. So I'm going to permanently label C with 6A. From C, I can reach E. So that's 6 plus 6, 12. So this will be replaced by 12C. The rest of the labels cannot be visited from C, so they will remain the same. Now, we have G with the least label this time. So I'm going to permanently label G. And then from G, we can reach H. So that's 8 plus 4, 12. 12 is smaller, so I'm going to replace this by 12G. And then we can also reach E plus 2. So 8 plus 2, 10. That's smaller, so I can change it with 10G. And that will become their permanent labels. As you can see, the shortest path from B to E is the path B to F, and then F to G, and then G to E, with a total path length of 10. So again, we perform Dijkstra algorithm just to be sure that that's the shortest possible length. So that's B to F, and then F to E, the path length of 12. So the total additional weight will be 5 plus 12, 17 if we use this pairing. Now, the other possible scenario is we can pair AB and CE. So if we pair AB, it's very obvious that the shortest path from A to B is the path AB of length 1. So we can have the pairing A to B of length 1, and then if we are going to pair A with B, then C will be paired to E. So what's the shortest path from C to E? So the shortest path from C to E obviously is the direct path. Because if you go around, so those paths will be longer than 6. So we have C to E directly. And the length is 6. So that will have a total additional weight of 7 if we use this path. Finally, we can also have the possible pairing AE and BC. So we have the pair AE and BC. So what's the shortest path between A and E? So A and E is this path or this path. So from those scenario, this is 17 and AC to E is 11. So that's smaller. Let's see if there's another path. We can also use this path A to B, and then B to F, and then F to E, and then F to G rather, and then G finally to E. If we add the path, we have 1 plus 5, 6 plus 3, 9 plus 2, 11. So the same as the path A, C to E. So we can choose any of them, but we can decide by inspection that the shorter path will be either ACE or ABFGE. So I'm just going to take ACE. So it's A, to C and then C to E of length 11. How about BC? What's the shortest path from B to C? B is here and then C is here. So I can go this way, that's 6, or I can go this way, that's obviously longer because that's 35. Or I can go here, but that will be significantly longer than 1 plus 5, which is 6. So by inspection, we can conclude that the shortest path from B to C is BAC of length 6. So B to A and then A to C. That has length 6. So total is 17. So of this possible scenario, the path or the pair with the smallest additional weight is scenario 2, where you have the path from A to B and C to E. Since that has the shortest or the smallest additional weight, the next step is to add that path to make this graph Eulerian. So you can now add path A to B and CE, these two. So if we now count the number of uh, edges or the degrees of each vertices, so this now has 4, this has 4, this has 4, and this has 4. So all of them has even number of vertices. So this time the graph is Eulerian. So now that you have a Eulerian graph, finally, you can now identify the desired Eulerian trail. So since we want the trail to start at A, and we want to traverse all the roads, so we just have to find a trail that will traverse all these road once and only once. Again, this is possible because we now have a Eulerian graph. So let's start at A. So let's say we want from A go to B. So let's take that road. So that's A to B. And then from B, we can go now to F. We can go to H. So this trail is not unique. So you can follow any trail for as long as you pass through all these roads once and only once, except for these additional vertices that we, or the additional edges that we have, the edges AB and the edges CE. But basically, that would mean that you just have to pass those roads twice. So from H, we can now go to G. And then from G, let's go back to F. So that we're done with that section of the map. And then from F, there's no other road to pass but go to D. And then let's go back here to G. From G, you can go to E. From E, so from E, you can go to D again. From D, you can go to C. And then from C, you can go to E. And then you can go back again to C using that same road. From C, you now go to A. You have no choice but to go to A. And then, so now you can go to D again, traverse AD edge, and then to B, and go back, use the same road again, AB, to go back to the original position A. So now, you were able to trace the graph passing through each road once and only once, except for those pair of roads that we go twice, the road AB and the road CE. So what's the total distance? So the original weight of the graph is The one that we computed a while ago is 109, and then the additional weight is 7. So that's 109 plus 7, giving us a total distance of 116 if we use this path. So that's how you find the shortest possible route using the route inspection algorithm, making sure that you pass all the roads from the initial position back to the original position again. So basically, the technique is to just make your graph Eulerian, adding several edges, but of course, choosing the smallest possible additional weight from all the possible edges that you can add.